I like cheat out this way. So this is a lecture for which I was given the prompt spheres. So there's a lot in it. This is a beautiful picture that I took shortly after I moved here. So hopefully you all get to enjoy some cool atmospheric phenomena like this while you're here. I'm going to give you a little bit of an intro about me just so you have some context for like what's in the talk. Like I said, there's a lot, so I had to pick and choose. So yeah, I'm a scientist here. I have a couple of degrees from the University of Oregon, including in theater. That's a whole story. So anyone else interested in the arts or dual majoring or got a non-traditional background, come talk to me. I love to chat and give advice. While I was doing my physics degree there, I was fortunate to do two different REUs, one at Northwestern and this very REU 9 years ago. So I was where you are at that time. So it's really nice to be back and on this side of the equation. During that REU, I worked on things with Earth atmospheric tides with Dr. Astrid Mauta, who's over at High Altitude Observatory. And that was really cool. And I liked it so much here that I decided to apply to grad school and was fortunate enough to get in. And I've been here ever since. So I got my PhD in 2023. And for most of that time, I've been part of the MAVEN mission, which I wanted to introduce because it's going to come up. My expertise is through that mission where we study the upper atmosphere of Mars. It's called Mars Atmosphere and Volatile Evolution. So a lot of my examples will be about Mars. Some will be about Venus, and I won't exclude all the other bodies in the solar system, but that's where my expertise is. And as a little bonus, there's me enjoying atmosphere in Utah. Let me just get rid of this message. Okay, so we'll start out really basic. What's an atmosphere? We might already know this, but there's a lot of different aspects that goes into it. I think of it as kind of this boundary region between surface and space on a planet, and there's an asterisk there because, of course, not every planet has a surface. And within atmospheres, there's lots going on. There's chemistry, there's climate, weather, dynamics, and we can also use atmospheres to study planetary evolution, although it may not be obvious how. I'll get into that a little bit later. Of course, atmospheres, we think, are probably also necessary for complex life to evolve. That's us. And we might even be able to use them to detect biosignatures or signs of life on other planets throughout the galaxy. So we're going to start out with a little game. And my question to you is, which planets in the solar system have atmospheres? So go ahead and think to yourself for a few seconds. Yes, I know Pluto is no longer a planet, but in my book, it still counts for the slide. I'm going to use the few seconds to take a drink of water. Okay. Using your fingers, show me how many planets on the slide you think have atmospheres. Nobody should be putting up 10 because there's only 9 on the slide. Okay. A wide range of options here. Seeing 7 is a popular number. 6. All right. Awesome. This is all true, and the secret is that they all have atmospheres, which may be a surprise. So 7 is a good guess because that's covering all of the planets that have like substantial atmospheres. But in terms of atmospheric studies, both Mercury and Pluto also have atmospheres, although we tend to call them like tenuous atmospheres or tenuous exospheres, which just means they're very thin and the dynamics are a little bit different than on the rocky terrestrial planets and the gas giants. So excellent job. If we think about what these atmospheres are like, we can group them in different ways. So of course we have the gas and ice giants here, which are mostly atmosphere, no real surface to speak of. The terrestrial planets, Earth, Mars, and Venus, and then these tenuous exosphere planets here, Pluto and Mercury. We can also group these in terms of what makes up their atmosphere overall, like in the greatest amount of a molecule that they have, in which case it looks like something like this. So the gas giants remain in their own group that are mostly dominated by molecular hydrogen, and Venus and Mars are over here in the CO2 dominated land. Earth and Pluto, interestingly, are in the group where they have mostly nitrogen in their atmospheres. And then Mercury is over here being somewhat special since it's got a very thin atmosphere. It's not really dominated by any one constituent primarily, except maybe oxygen. We can play this game with other bodies in the solar system. Some of these you probably have heard of, some of them maybe not. And you can think to yourself for a second, which ones do you think have atmospheres here? We can go a bit shorter on this one. And I've put the body that they orbit in the top right. Trick question. I put them on the slide because they pretty much all do as well. Although most of these are also tenuous exospheres. These are all different moons in the solar system, except for Ceres, which is a dwarf planet. Most of them have atmospheres except for maybe Titania, which orbits Uranus. We really actually don't know about that one, but so far the data indicate probably not. So the takeaway here is just there's lots of atmospheres to study in the solar system, and we have lots of techniques to do it. This is just a nice graphic to have on hand for reference. I think it's a little bit much for a slide, but I wanted to post it just to sort of reiterate what I've been saying. There's different molecules that dominate the atmospheres on each of the planets. So gas giants here, terrestrial planets, other bodies. And here included is also Titan, which was on the previous slide and is a pretty cool moon, which we will be sending a mission to in the near future. And of course, Mercury on the side, like I said, with a lot of different constituents in its very thin atmosphere. So now we're going to go on to thinking about how atmospheres form and how that process works. So we think that atmospheres have sort of two different, or there are two different types of atmospheres. First one is this idea of a primary primordial atmosphere. So when planets are forming in these clouds of gas and dust and maybe even rocky mineral material somewhere in the universe or the galaxy, they form this dense cloud that eventually flattens down because it's spinning in, and as it changes rotation rate to conserve momentum, it has to sort of flatten out into what's called the protoplanetary disk, like this one, which we have observations of in HL Tau. So the way that planets form, we think, is that they clear out lanes in this dusty, gassy disk and accrete material that way. So not only are they maybe forming surfaces, if they end up being rocky planets or cores, or if they're gas giants, they will collect the material into an atmosphere. And since these nebulae and protoplanetary disks tend to have a composition that's very similar to what we find in the galaxy at large, these atmospheres are typically composed of mostly molecular hydrogen, like I've been showing in the previous slides. So that makes up the primary and primordial atmosphere. I'm going to come back to this sort of later in the talk. Actually, no, I'm going to come back to it now. Sorry, I reorganized things and forgot. So I usually don't like to put tables on slides because it's like, ooh, I'm trying to read a table on a slide. But this is a nice simple one. I wanted to call out the top row. We think that primary atmospheres tend to be hydrogen dominated and reflect what was going on in the early days of the solar system, partially by looking at the gas giants in our very own system. So hydrogen and helium have a certain abundance in this protosolar nebula and in the protoplanetary disk. And if we look at those abundances across the gas giants and ice giants, we see the numbers are very, very similar. So we expect that these planets probably maintained their primordial atmosphere, and they've remained pretty much the same since they formed. Not exactly the same, but more or less. When it comes to rocky planets and other planets that are usually a lot smaller, we tend to think of these as secondary atmospheres. So these are atmospheres that are not dominated by molecular hydrogen, and they've usually formed a different way. And the ways that we believe that they formed is primarily through volcanism or other volcanic like outgassing activity, where stuff going on in the interior of the planet produces usually heavier molecules that can then release from the interior out to the surface and form a new atmosphere. Another possible way to get stuff into these secondary atmospheres is through volatile delivery from comets. So this is just like impacts. If you've got like some sort of comet or meteorite or something that's carrying perhaps water ice, if that crashes into your planet, it maybe has the chance to release all of those volatiles is what we call them, stuff that can change phase, and just release it into the atmosphere, and now it lives on that planet. There's a lot that's unknown about that process, because not only could impacts potentially deliver stuff to a planet, if they're large enough, they might even remove atmospheres from a planet. So this is a cool area of ongoing work, and one of our grads here is doing a lot of modeling related to that. Her name is Michaela, so if you see her, definitely ask her about this very cool topic. All right, so this is the Boulder Solar REU. So the next section is going to be all about different ways that the sun creates and affects atmospheres. And I've put a list here mostly so if these slides get posted, I think they typically do. You can refer back to them if you are curious. So this list here is not for reading now, but just to summarize what's on the following slides. Oh, the sun emoji looks very different in this version. It still looks nice though. So one of the biggest ways that the sun controls our atmosphere and climate is, of course, through its interaction with planetary obliquity, which is just the tilt on the axis around which it spins. So I've got a summary of those here. And this creates the seasons that we have on the planet. So on Earth, this probably feels pretty familiar. We have sort of a moderate obliquity tilt. And when a hemisphere is pointing toward the sun, then you have, of course, summer. And when it's pointed more away, then we have winter. Mars's obliquity is actually very similar to Earth. So we have very similar seasons on Mars. Definitely not a similar atmosphere. And there's different things happening on Mars that maybe don't happen on Earth. But the overall like progression of the seasons is similar. I am less knowledgeable about the gas giants, but they are pretty fast rotators with varying obliquities. I want to point out a really cool thing here is Uranus, which is tilted completely on its side. So its obliquity is 97 degrees, which is really interesting because that means one of its poles perpetually points toward the sun and the other is pointing toward away from the sun, or at least during part of its orbit. So this has very strange seasons by comparison, but again, I'm not an ice giant person, so I know less about that. And it might look like Mercury and Venus are not rotating here at all, but they actually are, and you can see if you can read the little numbers there. So Venus actually has a very, very long solar day. It's almost as long as its year, which leads to really interesting implications for seasons on Venus and what's going on in the atmosphere. This is the most technical slide I have, so don't worry too much. But this is about how the incoming solar radiation in the atmosphere sort of proceeds through it. So the idea here is you've got sun or a star, if it's a different stellar system, sending in radiation to the top of the atmosphere. And as that radiation comes in, it's going to interact with that atmosphere in various ways. Mainly, it has to go through it. An atmosphere to us, like visibly, is transparent, but it's not completely transparent to solar photons. So as they go through, they'll sort of run into molecules in that atmosphere. And whatever intensity the sun is coming in with, I naught at the top, is going to get attenuated to some extent as it goes through the atmosphere. We can quantify this with this small equation here. And basically, as you go through the atmosphere, that brightness gets attenuated by a factor of e to the negative tau, which is defined here. You don't need to memorize this for now. It's just basically a function of how many molecules are in that column of atmosphere, how far it's traveling through that column, and this sigma term, which is the cross section, which is basically like as the photon is going through, if it encounters a molecule, what's the equivalent area that it could potentially collide with. By the time you get down to the bottom of the atmosphere, however you want to define that, you've got a much lower intensity. But the secret here is that there's a dependence of wavelength for this radiation, the intensity of the radiation, and this tau, which is the optical depth. So this difference of behavior with regard to wavelength leads to a lot of different, I want to say like results or structure of the atmosphere, which I'll go into on the next couple slides. So one thing that comes out of this behavior is that you can get very different thermal structures in an atmosphere, depending on particular planetary parameters and how far it is from the sun and so on and so forth. So I put two here as an example for Mars and Earth. So we've got temperature on the bottom axis and height in the atmosphere on the y-axis. And it turns out that a lot of atmospheres in the solar system behave in a sort of similar fashion. Like the numbers are not the same, the altitudes at which things are occurring are not quite the same, but the overall structure is similar, except for Earth, which has this little bump here. So in general, close to the surface, if it's a rocky planet, there's a decrease of temperature with height, right? We've all experienced experienced this before, you go up to the mountains, it's colder. If you go up Everest, it's really cold. After some point, you run into this, it's harder to tell on this plot, but there's a region of the middle atmosphere, we call it, where there's sort of a leveling off, where there's not a great change in temperature as you go up in altitude. It's lower here on Earth. Earth is unique because it's got this warm layer in the stratosphere, which is caused by the ozone layer trapping additional heat. And then after some time, if you get higher up in the atmosphere, you start to see this increase of temperature with altitude in what's called the thermosphere. And that's because since the the atmosphere is getting thinner, radiation from the sun can come in more easily, get absorbed more easily, and the heating from the sun is very effective in this region. And that shows up in pretty much all of the planets. So as this radiation is coming in and reaching different altitudes, it's going to interact with the neutral molecules in the atmosphere and create an ionosphere. So this is just a simple plot showing the two parts of the atmosphere here from a model that we ran for Venus last year. On the left is the neutrals and the right is the ions in the ionosphere, as well as the electrons. This is maybe a weird plot if you haven't seen one like this before, but when we're doing atmospheric modeling or taking atmospheric data, we often put the altitude on the vertical axis so we can kind of have like a snapshot of how the density changes as you change that altitude. Whereas normally you might expect the altitude would be on the x-axis. So this is for Venus, so you can see that the most abundant constituent at these altitudes is CO2. And that leads to an ionosphere that's dominated by O2 plus and CO2 plus. As these ionospheres form, they also form with different distinct layers, and you can kind of see that on the plot. So you see these little bumps in the profile here at different altitudes, and these are all formed through different processes, and we have a very similar structure on Earth. So in Earth's ionosphere, we refer to these like different bumps or like density enhancements with different letters D, E, F1, and F2, and they're formed by different processes. So lower down in the atmosphere, there's a lot more chemistry going on. It's getting thicker. Radiation is still reaching it and driving this chemistry, but it's a lot denser, so these molecules can interact and do gas phase chemistry. As you get higher up, though, radiation starts to, it's easier to come in, but there's also, you have to worry about transport processes. So it's getting thinner, molecules are less able to interact, and you do have to worry about transport if you are, say, doing a model or trying to figure out what physical processes are controlling the structure here. We don't use the same nomenclature on other planets. At Mars and Venus, we use a simpler nomenclature. We just label the little bumps M1, M2, M3, or V1, V2, V3. So back to this idea of different behavior due to wavelength. The radiation coming in will reach different levels in the atmosphere, as I've been saying, depending on the wavelength. So this leads to this phenomenon of atmospheric windows. Let me move this little talk bar here. So on the top panel, we have on the left what the solar radiation looks like on Earth. So this smooth red curve is a black body curve. This is like some warm body like the sun emitting light, basically unobstructed. And then the filled in orange section here is what that radiation looks like basically down at the surface of Earth after the atmosphere has done some absorbing of that radiation. So you can see that there's little dips here, and these are absorption lines where the molecules have absorbed certain wavelengths of light that they can use to get energized or do other things. On the left here, we have then the radiation of Earth to space in the infrared, because of course the Earth is warm. It doesn't look like it's radiating to our eyes, but it does radiate in the infrared. So some of that heat gets lost out to space again in this little atmospheric window here. The next panel shows basically where these windows are without regard to necessarily what's causing it. So if you see a white space, that's where a window is. And if you see gray, the atmosphere is basically opaque to that radiation at that wavelength. So this leads to a lot of different impacts, I guess, for how we interact with the atmosphere too on Earth. So if you were to go further out to the right on this middle panel, you would see another window out in the radio, right? Because we can use radio down on the ground to communicate even to do astronomy. We have a window here in the IR where we're radiating. And then, of course, we have windows here in the visible so we can actually see things, which is great. Notably, though, we have the atmosphere is opaque in the UV, which is good because that is not, helpful for us continuing to live and not be burned. But when you look at how this overlaps with the emission spectra of different molecules in the atmosphere, that's when you start to see how this can really have some interesting climate impacts. So we've got water vapor here, carbon dioxide, and then some additional gases down here. And water you see has a whole lot of windows, but also a lot of points where it's opaque. So it's very easy to detect water vapor in Earth's atmosphere. Not as easy in planets around other stars, although we're very interested in that, of course, because we'd all like to know, well, some of us would like to know, are there aliens on other planets? As far as CO2 goes, you can see that this emission line right here, which sits at about 15 micrometers, is just outside of this atmospheric window. And this is where a lot of the greenhouse effect and climate warming comes into play. So we have enough CO2 in our atmosphere for this line to be pretty important, but as you can see, it's radiating where the atmosphere is mostly opaque, so that heat gets trapped. Okay, now I'm going to go into a little bit of a different section. We're going to start back up with climate like I was just talking about, and then sort of move to talking about how atmospheres interact with planetary surfaces and also maybe escape to space. This is maybe something not everybody would talk about with atmospheres, but even though I'm an atmospheres person, I'm also very interested in geology, even though I have no formal training in it. But there's actually, a lot of interactions with the surface that are important to consider, especially when doing planetary atmospheric studies or planetary geology. So let's go into that. So we were just talking about climate warming. This is sort of a big picture view of this process and how the surface is related to what's going on in the atmosphere and how that relates to what's going out to space. So this is called a Trenberth diagram. I guess it was popularized by this guy named Trenberth in the early 2000s, maybe even probably before, I think. This is just one example of a citation. And the goal here is to just capture all of these different inputs and outputs in the atmosphere and what's going on. So usually you'll have this big section here showing the incoming solar radiation. Some of it will get reflected out to space from the clouds or maybe even from the surface if it reaches all the way down. Some will get absorbed. There's various dynamics. There's thermal stuff going on here, phase changes that releases heat as well, or sometimes absorbs heat. And then from the surface of the planet, there's going to be radiation back out in the IR. Some of that then gets absorbed. Some of it gets reflected back from the atmosphere, like due to this like CO2 greenhouse warming effect. And then, of course, the atmosphere itself can also emit or do some absorption here. So you'll see these a lot for Earth and sometimes for other planets as well. And if you do all of this accounting with this sort of a scheme, you can use an equation here. I guess I had one more equation, sorry to lie to you. But this is very common in classes in atmospheric studies or astronomy, where you can calculate the equilibrium temperature of a planet using this sort of workup. And I'm not going to go through the terms in detail, but the takeaway is that if you do this accounting for Earth and you ignore the atmosphere, you come up with this value of 255 Kelvin for the equilibrium temperature. But the freezing point of water is 273 Kelvin. So this tells us right away that atmospheres are important because the average temperature of Earth is, of course, not negative 20 Celsius. It's a little higher than that. So if you add in the effects of the atmosphere, you come up with something more like 285 K, which is like 1520 Celsius, which is a little bit more reasonable and agrees with our experience where we have the ability for water to change phase between all of its phases. So on planets, I've been sort of talking about them so far in terms of 1D, like this is a sort of 1D type of plot. And my research, like I showed earlier with the Venus plot, is very 1D as well. But planets are 3D creatures, so there's a lot of complicated stuff going on. This is an example of how like the larger scale climate circulation works on Earth. So we've got these multiple different circulatory cells. They're called Hadley cells, and I guess as you go up in latitude, they may change their name to other types of cells. And you might have heard some of these terms before, especially with regard to different types of wind, like westerlies, easterlies, trade winds, and this kind of depends on where on the planet they are. And I really like this plot at right here because it shows how this climate and atmospheric circulation affects what's on the surface. So the circulation direction of these cells leads to areas of both upwelling, like here at the equator, and downwelling, like here at 30 degrees latitude. So as this atmosphere is welling up, it's getting cooler, which ends up producing a lot of rain. And what do we have around the equator? A lot of rainforests. It's not consistent around the whole part of the planet because there's also like smaller scale effects that can occur. But if you look at the sort of, you can just go to Google Maps, for example, and like look at the different parts of the world and you'll see this showing up. So similarly, we have downwelling here around 30 degrees. And what do we have at those latitudes? We have a lot of deserts. So like here in Mexico, we have like the Sonoran and the Chihuahuan Desert. And if you go around the planet, you'll see other deserts at those latitudes as well. Okay, now getting a little more fine-grained. This is one example of how atmospheres can shape like smaller scale features on the surface. It's one of my favorite examples because I think they're super cool, is these things called aeolian processes, which just means basically stuff caused by wind. So these are different types of sand dunes throughout the solar system. This one here is in Great Sand Dunes National Park. It's here in Colorado. You can go see it. I highly recommend you do if you can get access to a car this summer. It's very cool. This one forms because winds are coming from opposing directions. So some winds are coming over the mountains and some are coming from further west, and they sort of just collect sand that's eroded from the mountains into this little collection of dunes, which is a very unique place. And on the right here, this is also a photo of dunes from above. This is from the Mars Reconnaissance Orbiter's HiRISE instrument. This is a very high-res camera that we have to take pictures of the surface of Mars. And I just think that's so cool. HiRISE is a wonderful instrument. If you haven't like gone onto the website and searched through those photos, I highly recommend it. Oh, yeah, I also wanted to point out, we definitely know there are dunes on Earth and Mars, of course, but we think there are even dunes on Titan. We have some very interesting observations of those in the radio, and we have no idea what they're made of because Titan is so weird. It has a hydrological cycle like Earth, except it's not water, it's methane. So we've got methane lakes, we have methane rain on Titan. Titan does have rocks, but they're probably made out of water ice. So we really don't know what is making up these dunes. It's probably not like regular silicate rock like on Earth. It might be small water ice grains and like organics mixed in there. So this is a major question that hopefully the upcoming Dragonfly mission will address. This is just a quick slide to point out how these dunes are not just something we can observe actively. We can also see how they have existed throughout history by looking at the rock records. So this is two examples of lithified dunes, which just means dunes that have turned to rock. You can see them in Utah in the Navajo Sandstone Formation. Utah is really great because you can look at these different layers, and as you look further down in the layers, you're looking back in time. So this gives us a sense of not only what was going on in terms of geology, but also in terms of the atmosphere. This tells us that there was a very windy region that was building up dunes. And this is just one example. This here is also sort of the same type of outcrop, but on Mars. I think this is taken from one of the rovers. I forgot to put the mission there, but you can definitely find this online. And I think this is super cool. Like if these were not colorized and there wasn't trees on the Utah one, like could you tell which one was which planet? They look very similar. Sorry, I won't ever stop talking about Utah. It has so much cool stuff. Highly recommend you visit if you haven't. Okay, this is one more very cool example of atmospheres and surfaces interacting. This is on Io, which is a moon of Jupiter. So Io has a very thin atmosphere, like I mentioned at the beginning, primarily formed by volcanism because Io is the closest moon to Jupiter. It's very volcanically active because of all the tidal stresses it's under. So it doesn't have a lot in the atmosphere, but what little it does will be outgassed during, when volcanoes are going off. But then when Io goes behind Jupiter, so we have Jupiter between Io and the sun, we call that Io being an eclipse, and the whole atmosphere of Io well, maybe not the whole, but at least a significant portion of it actually collapses onto the surface. So this is mostly SO2 vapor becoming SO2 ice just because of this eclipse process. And this little plot here is showing one example of the observations that have revealed this. So you can see that there's a high amount of flux. I think this is the emissions that we're looking at from Io during when it's not an eclipse, and then as it goes into eclipse, that quantity substantially decreases as the surface temperature decreases. So very interesting process. I think this is pretty unique in the solar system, although similar like freeze out of the atmosphere may also occur on Pluto, although Pluto's year is so very, very long that we don't have a lot of data there because one season on Pluto lasts about 75 years. So you could spend your whole career studying Pluto and only see one season of it. So there's very limited data there. Sorry, that's one of my favorite facts about solar system science. And of course, we have the redness of the surface of Mars is a good example. We think that this is evidence of significant past oxidation on Mars. So Mars's surface is also very volcanic. It's very rich in iron. So as that was exposed over time to oxygen, that would have oxidized it to this red color. So another good example of atmospheres and surfaces interacting. I wanted to show this one as another example of like a surface to space connection. So this plot was made by my supervisor, Mike Chaffin, for a paper in which he wanted to show the impact of dust storms on Mars on the atmosphere as a whole and how we observe the impacts at the top of the atmosphere using the MAVEN mission. Kind of a long plot, so I need to take a drink of water. Okay, so this goes from the surface at the bottom here to the upper atmosphere at the top. So what he's showing here, the three lower panels are from the Mars Climate Sounder, which is a different mission, showing the opacity of dust on the bottom, the temperature in the middle, and then the amount of water ice in the blue one. So darker color here means more dust appears. This happens pretty regularly on Mars, although we still can't predict it. So as this dust storm appears, you see the temperatures start to go up because it's reflecting a lot of the existing radiation and warming up the atmosphere. This tends to melt the little amounts of water ice that do exist on Mars. You can see this also in the clouds that exist over the volcanic regions on Mars. So, whoops. So here on the left, you can see there are little clouds, these bright areas on top of the volcanoes, but as it gets warmer, those go away because they are sublimating into vapor. Then that vapor we can see with this panel here, which is from the Trace Gas Orbiter European mission. So darker colors equals more water vapor. What happens when you put water vapor up at these high altitudes on Mars? Well, that solar radiation comes in, breaks up the water molecules, and they release their constituent atoms, including hydrogen. Hydrogen can then travel up to the very topmost part of the atmosphere and releases Lyman alpha emission, which we observe with MAVEN here in the top plot. So lighter colors is more emission. So I just really like this plot because it's showing how a dust storm on the surface yields new observations at the very top of the atmosphere. So it's all part of this link system. Sorry, these were kind of two linked titles here. So this is all about how things may not stay on the surface. They may propagate up to the top of the atmosphere, but sometimes things do stay on the surface. So this is a very nice summary plot of evidence that we have on the surface of Mars for things that have been in place there throughout Mars's history, especially through atmospheric processes. So all of these different plots represent a different kind, points represent a different kind of material. The pink ones here are sulfates, which are produced through volcanic processes that were active early on Mars's history. There's also a few little green points, which are carbonates. So remember I said that oxygen probably oxidized the Martian soil over time. That oxygen typically comes from a lot of CO2 on Mars, we think. But if it did, where did the extra carbon go that was in that CO2? We would expect to see a lot more of these carbonate deposits than we actually do. So this is sort of an ongoing mystery. Is it buried deeper in the surface? Did it escape to space? Did the oxygen come from some other molecule? That's an open area of inquiry. I'm going to skip chlorides and silica, frankly, because I don't know much about them. But what I do want to mention is these blue points, which we have lots and lots of data for, are phyllosilicates, which is just a fancy geologist word for clay. And what do we know about clay? It forms in the presence of liquid water. So all of these deposits that we can look at in the geology tell us that in the past Mars was a lot wetter and had a different atmosphere in order to support that liquid water. Because it is not able to persist on the surface today, the atmosphere must have been different in the past. Okay, now we'll talk about loss to space. So I mentioned primary and secondary atmospheres in the beginning of the talk and how primary atmospheres may sometimes be lost, but sometimes not. So we have evidence that they may escape from smaller planets if they formed with those types of atmospheres. This is two sort of large, complicated plots. The left one is basically showing that on rocky planets orbiting M dwarf stars, so like red dwarf stars, the activity of flares on these stars can remove a whole heck of a lot of hydrogen from those atmospheres. So they suggest that if those planets are forming with primary atmospheres, it's very likely that they have lost all of that envelope very quickly. And the right one here is a recent paper by Park Lloyd, who was a graduate student here until recently, where they believe they have observed this hydrogen flowing out from some super Earth planets, so smaller than Neptune but bigger than Earth, in another star system. And the plots in that paper are a little bit complicated and not as easy to like read immediately. So I'm showing you here their modeling results where they use the data to constrain a model of atmospheric escape, showing that as time progresses forward, the atmospheric mass of these planets is decreasing. So they use this to argue that these planets are losing their initial hydrogen envelopes. But like I said, primary atmospheres don't always escape. Here in the solar system, we have several of them still existing. So that's great. We are very interested in knowing how primary atmospheres escape from rocky planets, as I've been saying, since this tells us a lot about their evolution. Like, did all the rocky planets form with these hydrogen envelopes and lose them? Does that, is that kind of a death knell for water on planets and habitability, or is it not? So this is definitely an area of ongoing research. When it comes to secondary atmospheres, there's lots of different processes that can either supply or remove them. This is more in my area of expertise since I study Venus and Mars. This is a cute little graphic made by a student of one of the professors here a couple years ago. And I'm not going to go through all these processes in detail, but just know there's lots happening in these types of atmospheres. And I added the idea of deposition here from that previous plot. I think it's kind of getting at it with chemistry here, but for me, this is a different sort of process. Since on Maven and in my work, we do focus a lot on stuff escaping from the upper layers of the atmosphere. I'm going to talk a little bit about that. So in terms of secondary escape, we tend to just divide it further into two main categories. There's thermal escape and non-thermal escape. And I'll just give you a little flavor of each of these. So thermal escape further includes two different processes. And these are often used to talk about the loss of hydrogen from these smaller rocky planets. So the first one is Jeans escape. And the way this works is just you've got some atoms in your atmosphere, you've got some molecules. And if it's hydrogen, especially, hydrogen is the lightest element. So it's very much more likely to escape than heavier elements. In the atmosphere, assuming that it's in thermodynamic equilibrium, which just means that it's dense enough that atoms are crashing into each other and exchanging energy, those atoms will have some distribution in velocities. Some of them are moving very slow, some of them are moving very fast, perhaps fast enough to exceed the escape velocity. And those atoms can just fly off into space, removing hydrogen from the planet more or less forever. This is more operating in like atmospheres without a huge amount of hydrogen. It's especially effective at Mars. It's not very effective at Venus and Earth because it also depends on gravity, and Mars has a lower gravity than those two. But on other planets that maybe have higher gravity and maybe have a much higher percentage of hydrogen in the atmospheres, you can get this phenomenon called hydrodynamic escape. So what this is if you've got a high percentage of hydrogen in the atmosphere, it'll be in the molecular form typically to be stable. And it's pretty okay at warming the atmosphere. It's not quite as good as CO2, but it's pretty okay. But the way it's different from CO2 is it's a terrible radiator. It is not good at recooling the planet. So as the planet gets warmer and warmer because of this buildup of H2, eventually it will start to throw off all that H2 into space in this grand river. So that not only removes hydrogen from the planet, it may also remove larger species that get sort of trapped in this flowing out river. So this is one way that we can remove secondary atmospheres. It may also be the process through which primary atmospheres are removed. So this one sort of straddles the line there. Okay, so these are both thermal. The next category is non-thermal escape, and there are so many processes in here. You don't have to memorize them or anything. I'm just going to give you a flavor. This is a cartoon I made for my dissertation showing all the different ways that stuff can be removed from an atmosphere, in this case Mars, because it was on Mars, through interactions with mainly the solar wind, which is, of course, a nice sort of jet of charged particles coming at the planets. So these charged particles, if they're moving, they'll create magnetic fields. They'll interact with the planetary magnetic fields and start to remove stuff to space. I wanted to highlight one process here called sputtering. So as this wind is coming in and interacting with the planetary atmosphere, besides these electromagnetic processes, it can also just truly slam into the atmosphere and knock stuff off physically. We have expected that this has been going on at planets for a long time, but we recently just finally observed it for the first time at Mars. This was written up by Maven's PI Shannon Curry. Paper came out 2 days ago, so very exciting, brand new science, fresh off the press.
New video.
Ooh, awesome. Excellent. I think I have some more videos in this talk, but not about that. So if I had found that, I might have put it in. So yeah, sputtering, very cool process. There's other processes like charge exchange, where you do a little swap-a-roo of the charges on some incoming hydrogen ions and ones in the atmosphere. There's also chemistry going on in the atmospheres, and if that chemistry involves ions or electrons, that'll grant extra energy to an atom and let it escape. There's so many processes. Just remember, ions are responsible for a lot of escape of planetary atmospheres. And there's one more process that falls sort of under this category, but is not necessarily involving ions, and that's giant impacts. So like I said in the beginning, sometimes impactors can deliver stuff like water to a planet, but if they're big enough, you might actually knock off a significant fraction of a planet's atmosphere into space. Did this happen on early solar system planets? We really don't know, but it's totally possible. So all these different escape processes can leave signatures of past climate in different isotope systems. So this is one where my expertise is relevant in hydrogen isotopes. As this escape is affecting the hydrogen on a planet, it will tend to leave an enhancement in the ratio of 2H to 1H, or deuterium to hydrogen. This process is happening at Mars, Venus, and to some extent Earth, but not really, because Earth doing a very good job of keeping a hold of its atmosphere and liquid water. So the way this works, since deuterium is heavier than hydrogen, it's less likely to escape. So over huge amounts of time, like millions and billions of years, hydrogen will escape preferentially, and you'll end up with an enhancement of deuterium to hydrogen when we compare it to the value on Earth. So this tells us that these planets probably lost a significant portion of their water that they used to have. It's not the only piece of evidence, but it is one of the pieces. On Mars, we also have the benefit of being able to look at the surface and see where water used to flow. We can send rovers there and like actually get samples and test them. Venus is trickier because it's very hard to go to the surface due to the high pressure and temperature. But because it has this D to H enhancement and we see a similar effect on Mars, we think this process probably happened at Venus as well. The water listed here today is just to give you a sense of the scale. So on Earth, we have several kilometers worth of oceans. And this unit gel global equivalent layer is just imagine that you spread out all of the water on the planet into a smooth ocean on the surface. How deep will that layer be? That's this number here. Venus today is super, super dry. That layer would be 3 centimeters, so hardly any water at all. On Mars, we're sort of in between. We still have a good amount of water ice on the planet and also water vapor, but significantly less than Earth. It's not just hydrogen isotopes that we can use to infer things about past climate. We can also use other isotope systems, especially the noble gases. This is two examples of some recent work. The left one is paper by Lammer et al. And what they're doing here is coming up with different scenarios for what might have happened in the early solar system on Earth specifically. Like, what was the impactors? What were the impactors that were colliding with Earth? What kind of volatile inventories did they have? What was going on with the solar flux that was coming in? And they sort of tweak all these different parameters. They run a whole suite of models. And then in order to check if the models make any sense, because of course we know very little about the early solar system, they use these isotope ratios here in these colorful lines. And they have these in their model, and then they try to assess whether the model output for these isotope ratios makes sense and agrees with the ones that we observe on Earth today. On the right here is a similar plot by my colleague Noor Al-Said, who is also a student in this REU at the same time as me. This is work that she did with Bruce Jakosky here, because she also went to graduate school here. And in this work, they came up with like a simple box model for Mars, looking at the water that we think it possibly could have had in the past, the water it has today, what the volcanic activity might have been, and then this R value here is related to that D to H ratio. So Nora ran a whole suite of models to come up with ones that match the D to H ratio of today to sort of get at what the water inventories are that satisfy this requirement and what the outgassing from volcanism could have been. Last thing, going back to Io, not only does atmospheric loss remove atmosphere from the planet it's being lost from, but it could also potentially impact the local space environment and other nearby bodies, which I think is super cool. So Io is very likely a source of this plasma torus feature that rotates around the Jupiter system. Due to Io's volcanism, it could be placing stuff into that torus. And it's even possible that some of that material could make it down to the surface of Europa, which is really cool. We don't have anything like that really here in the inner solar system. This also has really interesting implications for like habitability on Jovian moons. So are things living on Io? Probably not. It's got a really bad radiation environment for life, and the volcanism makes it pretty hostile. But if it's putting material onto the surface of Europa, maybe that material is making it down to the interior where there's a subsurface ocean. Very interesting open area of inquiry, but since it's so hard to go to the Jovian system, we don't have a lot of data about that. Okay, so I'm going to wrap up by talking about ways we pursue these atmospheric studies, just to give you a sense of the things, some of the things we do here at LASP and that are done throughout the community. On Earth, there are so many ways to study atmospheres. We have so many options. They're all so very different and very cool. We can look at tree rings to get a sense of what past climate was within the life of that tree. Like you can look at the thickness of the ring to figure out how much rain was falling or whether there was a fire season. We can take ice cores from the icy regions like in Antarctica and the Arctic to figure out what was going on in the atmosphere at that time. Like if you see like a layer of ash or dust, you might think that was, okay, that was a very a year when there was a lot of volcanism going on and spreading around the planet. It would be really cool if we could have these kinds of observers for Mars. I think we could learn a whole lot, but that is a mission that has not yet existed, so perhaps in the future. We've got weather balloons, we've got weather buoys. It's really great. On Earth, we have this whole network of like globally distributed weather sensors, but we just really don't have that for other planets, so we are much more limited in our approach. So there's sort of like three categories of like ways we can study atmospheres on other planets, at least in terms of observing them. So we can do planetary astronomy, which just means like Earth-based observations of solar system planets. We can also, of course, observe exoplanets, planets around other stars with these observatories. And usually these are on the ground in big telescopes in these domes, but we do have this really cool mission called SOFIA, which is a telescope mounted on a plane, and it observes in the infrared and produces really cool data. We of course have planetary missions. That's MAVEN. There's many more missions, but I only have so much time in the talk. And then we have space-based observatories here like JWST and Hubble. And these have been, well, JWST is quite new, of course, but Hubble has been going strong for like oh my gosh, is it like 25 years old now or more? Yeah. So these return awesome data, not just about the universe at large, but we can also use them for observing planets in the solar system, which is pretty cool. Now to talk about just some of the methods that are shared by these observational strategies. We use a lot of spectra to study atmospheres, and there's two types here, which you may have heard about before, and if not, that's okay. We've got absorption spectra and emission spectra. So I kind of mentioned the absorption spectra earlier. The way this works is you are looking at, there's a little diagram here on the top. You're looking at light coming in, passing through some sort of gas of interest, whether that's a planetary atmosphere or an interstellar cloud. It comes into your optical system, and then we use a detector to look at the dark spots in the spectrum, so to speak. This is an example for the visible. So those dark areas tell us where there are gases absorbing. We can figure out what is in that gas or whatever it is we're looking at. These are used especially at lower energies like infrared, microwave, and of course the visible too, and very useful for studying surfaces in the solar system and planets around other stars. We also have the emission spectra, where this is one that's on the top. And in this case, we're looking directly at light emitted by the gas of interest. So this is usually like electrons in the molecules in the gas get excited. Then when they eventually get de-excited, they'll emit a photon, which we can then observe. So in this case, instead of looking for the dark regions, we're looking for the lit up regions. So this is an example, again, from MAVEN with our ultraviolet spectrometer. So I made this plot because I am part of that team. And here we've got wavelength on the bottom and basically brightness on the y-axis. And we're looking at emissions from hydrogen in the Martian atmosphere. So this is hydrogen Lyman alpha and then deuterium Lyman alpha. Lyman alpha shows up everywhere. It's like one of the most common emissions in the solar system and the galaxy just because there's so much hydrogen everywhere. So very useful emission there. These types of spectra, you can use them with a lot of different wavelengths, but we use them a lot for ultraviolet and higher energy stuff. Okay, now we have a little movie. Let's see if it works. So this is about a technique called stellar occultations, which is where we are looking at a star as it sets beyond the limb of a planet. So it's you can do this from anywhere. You can do this from the ground, but we also do it a lot for missions. So let's see if we can play this. Bye. I'm going to skip ahead to where it actually shows the observation. I guess we can't full screen it. So you can see how the light changes here in the spectrum. That's our, no, stop. Sorry. Okay, that was our PI, Bruce. I also said our PI is Shannon. Bruce was the first PI to retire from an active NASA mission. That had never happened before. So that was a fun adventure that we had. I think so. Yeah, and then it passed to Shannon, and then Shannon became the first PI to go on maternity leave ever.
Yeah,
So they had to invent policies to deal with it. Shoot, now I've lost full screen somehow. How do I go back to it? Okay, there we go. Yeah, so stellar occultation, very cool process. Like I said, we do it with MAVEN. You can also do it from the ground and get lots of similar data sets with even different ways of like analyzing the features. I know for Pluto, they do this process, but then they look at, there's like a little bright spot as there's this dip due to the occultation, and that can tell them something about Pluto's atmosphere, which is pretty cool. No. Sorry. Okay, this was my backup slide in case the video didn't work. So now some additional examples of things we can do with missions. Missions are great because we can get in situ data, which just means like we are at the place where the thing we're observing is. Of course, not possible for many bodies in the solar system, but we have a wealth of this data from Mars, some from Venus, some from other planets. So on the left here, we have an example made by my friend Nisha, who's with us on the MAVEN team. And in this one, she was using the Maven static instrument, which is an electrostatic analyzer. So it looks at ions and charged particles in the atmosphere. And in this one, she was able to figure out how much O plus net flux was either precipitating or escaping from Mars. So here she's showing that there's a difference between the day side and the night side as you look across more or less the planet. This is in like weird coordinates called MSE. It has to do with the electric field, and I'm terrible at it, so I'm not going to go into it further, but this is a cool thing that we can do with this in situ data. Now, importantly, these in situ instruments, they're literally taking in the gas like to the instrument that they're observing. So it's really at one point in time. And then a plot like this is built up by looking at data across the mission. So I'm going to come back to this on, I think, the next slide. Similarly, with the rovers, we can get a really nice time series of data about the atmosphere, but only in one place, of course, because the rover is fairly limited. So this is a nice plot from Curiosity showing the water content and the relative humidity in Gale Crater over 1,200 sols, which is about 2 Martian years. Sorry, I keep hitting the microphone. I put magnetometers on here. I meant to remove this because actually I'm not talking about magnetospheres. I know you guys already heard about magnetospheres, but these are another cool in situ instrument that we can still use to learn things about the atmosphere by proxy. They're very small, they're very cheap. Put them on every mission. Love them. Okay, so one more example of a cool in situ sort of process. I don't think this one requires sound, but I wanted to show it because it's awesome. I'm just going to mute it. So this is a cool video showing the descent of the Cassini-Huygens probe into Titan's atmosphere. So thus far, this is the only like in situ data we have from Titan at all. We of course have other observations in the radio, but this is pretty unique. Oh, it is making sound. Okay. Anyway, so this is sort of like the view down towards the planet. They had a camera on the descent probe, and you can see a little cartoon of it here. And then if you look on the top left, hopefully you can see it's a little small, and I keep not being able to full screen it, but this is showing the actual data being recorded by the sensors on the probe as it goes down. So this is recording the altitude that the probe is at, how fast it's moving, what the wind speed is, where it is, air pressure, air temperature, and various other parameters about the probe. So it's sort of building up the view as it goes down. I'm going to skip ahead a little bit just so we can get to the cool part where it hits the surface. So you can start to see things coming into view. Titan is not unique in this, but it is, it's pretty cool that it's covered in this dense photochemical haze. So if we look at it from out in space, it has this very sort of opaque yellow appearance. We can't really see anything on the surface. So that's why it was so awesome that we were able to send this probe down to the surface and get some initial look at Titan to sort of entice us. And of course, now we're going to have a new mission, Dragonfly, that will go to Titan and send an actual octocopter to fly around Titan, which is quite an endeavor. And I'm very excited to see what they come up with. All right, we're so close. We're so close. We're about to hit the surface. Bam. Okay, there we are. So probe has hit the surface and collected these images of the surface. So it looks pretty desolate, but like I said earlier, these rocks are probably not silicate rocks, but water ice rocks, which is possible because Titan is so cold. And of course, this one over here is the moon. This is not Titan. We did not walk on Titan. I'm not sure why they put that there, but probably for comparison. Okay, so probe's great. They give you really detailed information, but at one place and at one time.
So did the first
It went onto the surface and recorded the descent profile and then recorded for a little while. I'm actually not sure how long it lived. I can't recall, but the data set is pretty limited and it didn't move around or anything. It was just limited to where it landed. Yeah. Yeah, and it didn't like burrow down or anything, although that would have been super cool. Okay, I think I have just a few more slides here. I don't know why forward seems to start the video. It's very weird. There we go. Okay, so I've been talking a little bit about like where we can get data and to what extent. So this is just to sort of hammer that point home. So on Earth, we have so many we have so much data. We have so many sensors. This is just an example from Purple Air, which tracks the air quality, which we use a lot during the summer. It's simple to get a sensor. You can just buy one and put it up at your house. So we have lots of data. We are covering the whole planet. We can get these measurements simultaneously, and we can do them for very long times because, of course, our climate is stable. It's not quite as hostile as, like, say, Venus. But so this is kind of like the goal. This is how much data we would like to have about other planetary atmospheres. But there's always a trade-off. So I've sort of showed how these do for these other observation types that I mentioned. So with MAVEN IUBS, we're an orbiter around Mars. So we have pretty good spatial coverage, but we have to look at very long times in order to build up that spatial coverage. But like each observation is not necessarily at the same time as a different observation. So there's a big spread in time. So we have to build up those data sets in order to get a global picture. By contrast, Curiosity has very poor spatial coverage, right? It's sitting in one spot in Gale Crater. Maybe it moves like 100 kilometers over its lifetime. I don't actually know the exact number. But you can form this really nice time series, which is, complementary to orbiters to some extent. And similarly with the probes, poor spatial coverage, not very good in terms of long time baselines to build up the data set, but you can, all of this data recorded by the probe is pretty low spread in time. So this is a constant challenge with studying other planetary atmospheres. It would be awesome to have like a global weather sensor network on Mars or Titan or whatever, but there's a lot of technical and monetary challenges there. So since, we're limited in data that we can get and observations we can make, we do a lot of work with modeling to study atmospheres. This is by no means a complete summary of all atmospheric models. This is just some examples. So we do a lot of work with 1D photochemical models. This is the plot from my work that I showed before. This lets us study the chemistry in detail on sort of an global average basis. We also have a lot of different 3D models. So the one at the top right is sort of studying the exact trajectories that individual particles can take in an atmosphere. And these two models work together fairly commonly. A lot of work, especially on Earth, is done with 3D GCMs or general circulation models. Sometimes they're called global climate models. And this is kind of an attempt to like throw the whole kitchen sink into the model. Like, let's model every process we can. We're going to model it as a sphere. We're going to have transport going horizontally and vertically in every which way. And we try to put in all the physical processes that we can. So we do these for Earth and also for Mars, for Venus, pretty much every planet, there's a version of one of these models. And then another type is these mesoscale models. So these are also 3D models, but they're not quite as extensive as the GCMs. And they cover like a limited region on a planet. So this is one example here that's covering the US. They tend to be used a lot for weather forecasting, especially on Earth, but we do use some of them at different planets as well. Last little part about observations, getting into biosignatures. You might have saw on one of the first slides, like, I would love to know if there are aliens out there in the rest of the galaxy. That would be super fun. So many other people are interested in this as well. And one way we're trying to get at this question is by observing gases in atmospheres around other planets, around other stars. So we breathe oxygen. So far, oxygen is kind of our best guess for, could this be a biosignature? If there's oxygen in another planet's atmosphere, does that mean there's life there? How about complex life? Trouble is, it's not a unique biosignature. So you can produce oxygen through other processes that don't involve life. Like Mars has not a huge amount of oxygen, but some. And that's all formed through basically geological and chemical processes in the atmosphere. So some folks, including Vicki Meadows at University of Washington, have done a lot of work to come up with, okay, if we observe oxygen in an atmosphere and we observe other molecules, like which ones indicate it might be a false positive, what might we observe that would tell us it might be a real signal? So there's a lot of work being done here, including with other molecules I'm not going to talk about. But overall, so far, we have no particular gas in an atmosphere where if we observed it, we would say that's definitely life. There's no like sufficient gas yet identified. But on the topic of sufficient gases, we can talk a little bit about some of these observations, especially in recent work, that are very controversial. So you might have heard about some of these in the news. You might have even looked at some of the papers. There's been several of them on Mars, Venus, and an exoplanet. So there's been reports that there is a sort of seasonal cycle of methane on the Mars surface. This was detected by the Curiosity rover. This is very interesting because methane is a fairly unstable gas. It should be broken down by sunlight, but it's persistent in these data sets and it has a little cycle. So people have been wondering, is this indicative of methanogenic life like in the Martian surface? Very controversial. I'm going to just say I don't really believe that this is a signature of life on Mars. We also have the Trace Gas Orbiter orbiting Mars, and it was specifically designed to look for gases like this in the atmosphere, and it has not observed a methane signature. Of course, you might say, well, the rover is down here on the surface, the Trace Gas Orbiter is hundreds of kilometers up, like maybe it's just not seeing the same thing, but they're working very hard to try to reconcile that. We just haven't gotten there yet. So very controversial. There's also this issue of phosphine on Venus. This came out in September 2020, so at least we were entertained, while we were sitting in our houses alone. So phosphine is a gas that's used by life. I don't know a huge amount about it, but folks were suggesting that this indicated that maybe there's some kind of life existing in the Venus clouds, or even maybe lower down, and it's traveling up to the cloud region. But as far as I can tell, folks who have reanalyzed this data set, looking at this absorption line of phosphine, have said, the signal is really low. We don't really believe it. So this is kind of an ongoing argument in the community as well. And then most recently, there was supposedly this detection of dimethyl sulfide, which is, I think, a compound produced on Earth by like plankton in the ocean. So this was observed on an exoplanet, supposedly. And I know a lot less about this method, but what I do know is that if you start talking about DMS and K2-18b to any astronomer, not any astronomer, many of them, they'll start to sort of groan. So I think this signal is also pretty weak. It's hard to verify whether it's believable or not. So personally, I think if we're going to find aliens out there, it's probably going to be on like Enceladus or something where we've got, evidence of a subsurface ocean, and hydrothermal vents. Be cool if we could find evidence in an exoplanet, but it's a pretty hard measurement to make. I just want to wrap up with a few open questions about all the planets we've been talking about. So on the rocky planets, we have some similar questions and some different questions. So basically on all of these, we have this question about the faint young sun paradox. And I didn't want to go into this in too much detail, but the idea is basically that when the sun was a lot younger, we expect that it was somewhat dimmer. It was only putting out about 70% of the flux that it puts out now. And yet, on early Mars, we know that liquid water was running over the surface. We think it may have been present on Venus as well, and it was definitely present on Earth. But all these planets would have been colder if the sun was dimmer. So what's the resolution there? That's an open area of inquiry. And sort of relatedly, we don't understand what the ancient atmospheres on these planets were like really at all. We have like some idea of Earth because we live on it. But as far as Venus and Mars go, it's pretty much all down to, not all, but a lot of it is modeling, and it's very hard to constrain this problem. So we really don't know what was going on ancient times to support the liquid water or whether there was life there, so on and so forth. Each of these planets also has some unique questions that I've listed down below. Like I said, for Venus, we don't know if liquid water was ever present at all, so that's a major question. We know it was for Mars, but we don't really understand like how the atmosphere has escaped over time. We know it's escaping today. That's the focus of the MAVEN mission. And we expect that it was probably higher in the past, like there's greater escape in the past. But again, that comes down to modeling because it's very hard to get the geological evidence that we need or the atmospheric evidence. And of course, on Earth, we have this issue of climate change and whether that's going to be a major problem or a minor problem or how we're going to deal with that. Some questions about the outer solar system. There's obviously way more than this, and I'm not an outer solar system expert, but these are the ones that I'm aware of. Like I said, Jupiter is a gas giant with a primordial atmosphere, so it's very similar in composition to the solar nebula, but there is some enrichment of these heavier elements compared to the sun, so we don't really understand how that occurred. And we don't really understand the nature of the Great Red Spot. Like, this is supposed to be some really big storm system, and we know a little bit about it, but we don't know how far down it goes or really all about the dynamics that are happening. With Titan, very intriguing, of course. That's why we're sending a mission there. We would love to know if it's habitable by methanogenic life, if there's implications in what we can learn about like origins of life, like if some of these processes could happen on early Earth. And like I mentioned, we think we have observed sand dunes there and we have no idea what they're made of. That's just my little pet interest there. And like I mentioned with Pluto, the year is so long that the whole time we've had a space program, we've only seen one season of Pluto. So we really don't know anything about its atmosphere at other times of its year, beyond what we can deduce with modeling. So I don't do Pluto at all, but I think it's fascinating. And there's still a lot of questions about how its atmosphere works. There's a lot of dynamics that go on with sublimation of nitrogen ice off the surface and condensation. And a lot of that action is happening here in Sputnik Planitia, which is the heart of Pluto. But there's still a lot of mysteries there to be found. Okay, I'm just going to leave you my summary points and enjoy your summer in Colorado. I certainly did. And I hope you have a great time and get a lot of good work done. Thanks for listening. I'm sorry, I forgot to say at the beginning, you could have interrupted me at any point, but I'm happy to take any questions or comments or whatever you want to say.
Question for our speaker?
Yes.
Yeah, so with the Martian atmosphere, so I know that it kind of has one, but each way, do you know how with like the remaining magnetic fields, how does it interact with that?
Yeah, this is a great question, and the answer is it's complicated. I think you heard a little bit about magnetospheres already. I don't know who gave you that lecture, but I will say this is definitely an area that we are working on actively. In some cases, the crustal fields on Mars will enhance escape, depending on like the configuration of the interplanetary magnetic field and like what the atmosphere is doing and whether it's able to flow along those lines out or whether it's more likely to get trapped if the field lines are closed or open. So sometimes escape can be enhanced by these fields. Sometimes they may slightly protect a small area of the planet. Mars is tricky because it's got these crustal fields that are just sort of not randomly, but like distributed in sort of an arbitrary way, I guess, which is not the same as random, over the crust. And it's also got this intrinsic magnetic field. And I think I had a slide on that before I realized you'd already had like a magnetic field lecture. So this also has some impact as well. But I don't think we can definitively say yet whether magnetic fields only enhance escape or only protect. I think it's kind of in between. We do expect that like with a full dynamo magnetic field, maybe this is helpful in some way to the maintenance of an atmosphere because we have a full dynamo, a magnetic field here on Earth and we have an atmosphere, so that's good. It might have to do with like the timing of the magnetic field and when the atmosphere is formed and when it's being lost. So lots of open questions there. If you are interested in magnetic fields and ion processes, I think that's a great area to go into. It seems like there's always work to be done there, and you can do this kind of work on lots of different planets. Even like with Mercury, there's not very much of an atmosphere, but they do have, Mercury does have like some sort of, I think, induced magnetic field. If that's totally wrong, then just ignore me, but I believe that you can still have some of that going on since you do have particles in the exosphere that can be ionized. And yeah, all the gas giants have these magnetic fields as well that are going to provide plenty of problems to work on. Cool. Any other questions?
Thank our speaker again.
Thanks, guys.